Hello, this is a video on our last experiment for Physics 71.1, which is about the simple pendulum. So in this experiment, there are two objectives. Mainly, first, so you are expected to determine the factors affecting the period of oscillations for a simple pendulum for small amplitudes. So this part, the simple pendulum for small amplitudes, will be very important to note for this experiment. So secondly, you are to determine the acceleration due to gravity in Earth using a simple pendulum method. So while we already know the value of this acceleration, maybe from Physics 71 lectures or from previous experiments, we can use the simple pendulum method to also achieve this goal. So what is a simple pendulum? So basically, a simple pendulum, as shown here in this figure, it's an idealized model consisting of a point mass suspended by a massless unstretchable string. So we say idealized because we have simplified a lot of factors compared to a real-world pendulum. So for example, I considered my mass to be a point mass. So we won't have any factor in its moment of inertia. And we have a massless unstretchable string, which is not always realistic. So despite this case not being realistic, the simple pendulum model is used because it serves as a foundation in understanding those real-world phenomena or physical systems. So some examples of real-life situations modeled by this simple pendulum are a person on the swing and the wrecking ball on a crane's cable. So just in case that you are not able to imagine what a simple pendulum would be like, so we have here a prepared short video. So in this video, this person has a pendulum bob hanging by this string. So in this initial state, the pendulum bob is perfectly pointing downward. But the person will now displace the bob at some point and let it go, and the pendulum will now oscillate. The bob will be kept in this oscillation motion due to the presence of a restoring force. So going back to our manual, so again, when the bob is pulled to one side of its straight down equilibrium position, it will experience oscillation motion. So when you displace the bob, you are displacing it with an angular displacement, theta. So the bob will move until it reaches a maximum amplitude, and it will then return to its initial position after some time t, called the period. So again, the period is the time needed for the pendulum to move back to where it came from and not just an end-to-end time. So in the simple pendulum, I mentioned earlier that we have a restoring force. So this restoring force is negative mg sine theta. So this might be familiar to you. So this is just the component of your weight. This is just one component. Here, m is your mass, g is the acceleration due to gravity, and theta is your angular displacement. So for a body to move in simple harmonic motion, the force it experiences must be restoring, and the acceleration of the system must be proportional to its displacement from equilibrium. So these are our two conditions. However, given our condition of negative mg sine theta, our condition will actually fail because the acceleration in this case will be proportional to sine theta and not just theta. So we find ourselves in a conundrum here. So how do we resolve this problem? We can use a small angle approximation. So for very small angular displacements, sine theta is approximately equal to theta. So I'm not sure if you all have encountered this small angle approximation, but I can demonstrate this to you graphically. So going back to our browser here, I have graphed here the graph of a simple line y is equal to x and a standard sine function y is equal to sine of x. So as you notice, the regular forms of these graphs are really different from each other. So you have your line here, which is just straight, while your sine curve is oscillatory as it should be. Now, the small angle approximation states that these two functions are approximately equal at small angles. So we can do this by zooming into the graph to see the small angle approximation. So once we have zoomed in enough, we see that at this region here, this very small region around the origin, the sinusoidal curve and the line will have exactly the same form, which makes this small angle approximation possible. So if I zoom in even further, I will even have just one graph. All right. So going back to our manual, so with this approximation, we can write f is equal to negative mg theta. Now, theta is an angular displacement. So if you recall some basic or previous mathematics that you have encountered, the angular displacement can actually be expressed in terms of an arc length. So the arc length is a relationship between your linear and angular displacements. So in this particular case, theta can be expressed as x, a linear displacement, over L, which is your pendulum string length, which acts as your arc length. So in this case, we can rewrite the force as negative mg x over L. So we can then assume that the oscillatory motion is only along the horizontal. So by using Newton's second law, we can write our forces in this manner, which is now in the form of a simple harmonic differential equation. So the restoring force is now then equal to the proportion of the small displacement with the force constant of k is equal to mg over L. So using this force constant, we can now derive an expression for the angular frequency as follows. But what we really need is the period of oscillation, which we will be using for this experiment, which we derive to be T, capital T, is equal to 2 pi over omega, or 2 pi square root of L over G. So here again, we recall that the constant 2 pi is multiplied to the square root of my pendulum string length, small letter L, divided by the acceleration due to gravity, small letter g. So this derivation shows that for small angles, the motion is a simple harmonic. So one important observation here is that for the pendulum period, there is no term that corresponds to the mass of your pendulum bob. This means that for whatever variation of mass you make to your pendulum bob, the oscillation period will still be the same for a simple pendulum model. So the period is determined entirely through G and L. So now let's move on to our experiment proper. So here we will be using a simulation website. So this link is clickable from the manual and you can use it. And if you click this link here, it will lead you to this following website. So once you have reached this particular website, you can click play here, which will prompt this loading screen and this interface. For our experiment, we click intro. So now we have our simple pendulum interface. So let's explore this a bit. So we have here a set of tools and a lot of buttons that we can use. So let's first start with the lower left portion. So we have here our checkbox for a ruler, a stopwatch, and the period trace. So the ruler is movable as well as the stopwatch. You can click on it to drag it wherever you like. So next here, have here at the lower middle, We have here a button for a double pendulum or a single pendulum. In this experiment, we only consider the single pendulum. And we have here your stop button, your pause, normal and slow mode. You'll be using this later. And lastly, we have here our reset button, resets the entire interface. But I want my ruler and stopwatch here. And lastly, we have the sliders portion at the upper right. So these slider options allow us to vary our pendulum string length. So if I can just drag this around, and the pendulum mass. So it's represented as making the mass bigger. I have here my gravity slider. I can change the gravity to whatever value I like. So for example, I can drag it, but there are also set values for Moon, Earth, Jupiter, some planet X that's unknown, but we just use Earth. So lastly, we use the friction slider. So to simulate the effect of friction on our pendulum. So for this experiment, that we will be using is our friction slider will be set to 5. So how do we actually make your pendulum move here? So basically, the best way to measure your periods would be to first pause your simulation and then set your pendulum to some angle displacement before making it move. But let's explore that part later during the proper procedure portion. So procedure part 0 will be familiarization with FET simulation. So you can also read this, but I basically did this part already. So now let's go to part 1. So determining the effect of the string length to the period of oscillation. So let's try to make a sample measurement on this part. So make sure you are in the single pendulum mode. So you are already here. So in the LM panel, set the length to be 0.2 meters and the bob mass to be 1 kilogram. So if I want to do this, so I set this to be 0.2 meters and I set the mass to be 1 kilogram. So align the slider for the friction to the 5th tick mark. We have already done this. So this will be applied to the entire experiment. So in the RSP panel, check the stopwatch. We've done this. At the bottom right, choose the normal mode, then click the pause button. So we already have the normal mode and the pause button. So next, we click and drag the pendulum bob to set its initial position. Choose an initial angle that's less than 5 degrees. So let's try to choose exactly 5 degrees so I don't measure anything similar to your experiment. So just choose any value less than 5. So in this particular case, if I displace my pendulum, my angle is actually measured as I move my pendulum bob along. So if you notice, the number comes up here at the circle, the half circle portion. So from here, we have 5 degrees. I want it at 5 degrees. So next, click the play button to start the swing and the stopwatch. So record the time it takes for the pendulum to make 10 oscillations, and based on this measurement, determine the experimental period of oscillation. So for this case, I'll have to click play. So my pendulum is already displaced. So I click play here. And now I will measure the time for 10 oscillations. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay, given this measurement, I measured 10 oscillations to occur in a period of 9 seconds. All right. So to stop the measurement, I just paused my interface again. And if I want to reset my measurements, I just press stop and stop the stopwatch or reset it to set the time back to 0 for my next measurement. So here, I have to complete 3 trials of the same measurement to find T best. So T best will be the best estimate of my period, which will be the average of the 3 trials. So next, I will be recording this result in table W1, and I'll compare the experimental period with the period calculated using equation 5. So this should be equation 5. So just for reference, equation 5 is our boxed formula here. So this is the theoretical period, which is based on, again, L, which you set in the experiment, and G, which you will be setting to be constant as well. So next, you'll do the same measurements for 0.4, 0.6, 0.8, and 1 meter. So part 2, we're to determine the effect of the mass on the period of oscillation. So in this part, you'll basically do exactly the same instructions as before, but this time, you will be fixing your pendulum string length at 0.8 meters, and now vary the mass at 0.3, 0.6, and 0.9 kilograms. So using this data, you will be completing table W2 of the data sheet. So lastly, you will be plotting the acceleration due to gravity on Earth, determining it from the plot. So using the results from table W1, you make a plot of T best squared ito, versus length. So how do you relate this to equation 5? So the actual instructions, you already know this by now. So I'll skip it. So you'll compare this lastly with the experimental value, or the theoretical value rather, which is 9.81 meters per second squared. Okay, now we move on to our actual data sheet. So the period dependence on length will be on table W1. So you will be measuring 10 trials, or 10 oscillations for 3 trials with varying lengths. So here, I want you to record each period that you have measured when you have done 10 oscillations. But for your T-best, what I want you to do is take the average of the 3 trials. So that's the instruction. But also make sure that your T-best is only for 1 period of oscillation, not 10. So what you want to do here is divide your average of the 3 trials by another additional factor to make the average of 10 oscillations to be just the average of 1 oscillation. So take note of that. So you also have your theoretical period from equation 5. So you can also calculate that. So note that your measurements must have uncertainties. So in this case, your uncertainty would come from your stopwatch. So going back to your stopwatch, what is the measurement that you can use to get the uncertainty? So you go back to all the way to experiment 1 to get this uncertainty. What is the uncertainty of a digital device? So you'll have to recall that piece of information. And next, you have your period dependence on mass. So again, you'll do the same as what you did in table W1, but this time you vary the mass and fix the length. So you also have here your figure 2, which is the plot of T squared versus L. So note that the square is important here. So take note of that. And lastly, we arrive at our questions. So these are guide questions that you can use in the future. So we have a total of 3 questions here. So first, you're to draw the free body diagram of a simple pendulum. So I can give you a hint here. So you can refer to Physics 71 lectures. So you can determine the free body diagram of your simple pendulum. And number 2, the motion of the simple pendulum is approximately simple harmonic. What are the conditions that make a motion simple harmonic? So we already discussed this earlier. So you should already know this. So number 3, suppose that there are 2 identical pendulums. So pendulum 1 is in a room filled with air, and pendulum 2 is completely submerged in water. So is there a difference in the period of oscillation between pendulum 1 and 2? So to answer this question, a hint that I can give you is what happens if there are additional forces acting on the pendulum. So what forces are different if the pendulum is in air or water? So that is a hint for question 3. So this concludes our manual. But before we end this video, I would first like to just reiterate that the requirement for experiment 7 is not this worksheet, but rather it is a summary report. So I'll show you a sample summary report. So this is a particular example of the summary report. So this is actually a sample using the free fall experiment. So basically, this is a paper, a science or research paper. So it is in paragraph form. So you have a standard introduction, you have an abstract, you have your results and discussion, and the data is not just answered, the questions are not just answered, but they are incorporated in a way that you have a actual discussion occurring. So you have your tables here and graphs represented as a paper, and all the way down to a conclusion. So what is the conclusion that you can draw for this particular experiment? And of course, you also have references. So any information that you will be using for the summary report would have to be referenced. So I will give you a copy of this particular example, so you have a somewhat a short basis on how you can write your paper. But I will also make a separate video that serves as our summary report writing workshop, which can be used for our writing. So if you have reached this far, thank you for watching and good luck with the last experiment.